My name is Thorben Hu. I'm associate professor for performance neuroscience and sport neurophysiology at the LUNEX University in Luxembourg. Maybe you've heard about Luxembourg. This is a very small country in the center of Europe. So sometimes you miss about that. But I'm working there as the program leader for the Master in Sport and Exercise Science and the leader of the research group in neurophysiology and motor control. And today I would like to present on visual evoked potentials. So also some research that we did some years ago in 3 different parts. So we will start with some information about the visual evoked potential itself, what we have to consider when measuring or trying to measure visual evoked potentials. And then in the second and third workshop, we are more going into practice. So what are some kind of processing pipelines that we can use to get a visual evoked potential out of our data? Good. Then I would say we can start. Just a quick overview what I would like to do in this first part of the presentation. All right, here we go. So as I said, a quick overview. So I will start with the visual system very briefly, however, something that we should consider. So especially the M and the P cells, because this has a huge influence on how we design our stimuli. Then also the stimulus selection for visually evoked potentials, because we have different visual systems in the brain that we can address with different types of stimuli. And this is also something that we have to consider when designing our experiments. Some EEG and experimental setups. I think the EEG part I can do very quickly. I think everyone is familiar with that. Okay, I did. Okay, let's do that again. Now? Yeah. Wonderful. You are sharing this one. Wonderful. No. Oh, no, it is. Okay. Yes. Okay. Okay, so some EEG and experimental setups, and in the end, if we have time, I will show you some characteristics of the contrast and the motion VEPs, and so the 2 types of VEPs that we are typically investigating. So where we are in the brain is basically in the visual system. Of course, we can also measure other types of evoked potentials. So we can have auditory evoked potentials, somatosensory evoked potentials. Here we want to focus on the visual system. And especially what we are measuring in the end is everything from V1, so the primary visual cortex, or secondary visual areas. Okay, so overall, we have more than 30 visual areas that have already been identified in the central nervous system. So later on, we will specifically focus on 2. So one for contrast and color information. So the primary visual cortex and the visual motion sensitive area MT, as the name implies, for motion information. Maybe a few information why the visual system. Well, the visual system, of course, is the dominating sensory system that we have. It is estimated that around 80% of our information from the environment are processed by the visual system. More than 30% of the cortex are 24/7 just in processing visual information. If you compare that to the auditory system, there is only 2%. So it is apparently the dominating one. It is also one, or maybe the best investigated sensory system that we have. So if we have a look at the literature, we have thousands of studies on the visual system, especially also on the visual motion system. So that's quite interesting. And since I'm coming from this field of sports, I've investigated the visual system, especially in the field of sport. We have to consider that it is the slowest one. So when we compare it to somatosensory information, when we compare it to auditory information, the visual system is way slower. Still, we highly depend on the visual system. So 80% of the information is visual that we process. This just as the background. So if there are questions, I think you can always interrupt me. Let's come just very briefly to the start of the visual system, so to the retina, because this is important later for selecting the visual stimuli and the characteristics of the visual stimuli. So basically, it looks like that. This is nothing new. We have the rods, we have the cones, and so on and so forth. The central part of the retina with the fovea, the more peripheral parts. what I would like to emphasize here are the two different types of cells that we have to consider. So we have the so-called P cells, so the parvocellular cells, which are located especially in the center, so around the fovea. And we have the so-called M cells, magnocellular. Okay, stands basically for small and large. Okay, so small receptor fields, large receptor fields. In the center, we have the P cells. More in the periphery, we have the M cells. And what later becomes important is especially the distribution of these cells, because we see that in the center, we have a very high density of the P cells. Okay, so if you have a look at the graph, I've tried to highlight that here in blue for the P cells. Okay, so at 0 degree of eccentricity, basically, so at the very center of the fovea, we have a lot of P cells. Okay, so this is why we have a very high spatial resolution for everything that is on our fovea. While in the periphery, we have more of these M cells that peak of around 20 degrees of eccentricity. Okay, so these two different types of cells, and you will find this later when we come to the design of stimuli for visually evoked potentials, that we have to consider exactly this distribution and the localization of these two different types of cells. Because what do we want? In the end, we want to investigate the visual system, and we have to ensure that these two types are, let's say, not overlapping in our visual evoked potential. So with our visual evoked potential, we are either addressing these P cells, so in the center of the fovea, or we are addressing the M cells. Okay, so the P cells, especially with contrast and color. Okay, so these two types of information that is processed by the P cells. And for the M cells, especially motion. Okay, so we have to think about how do we design stimuli that maximize the contribution of the P cells while minimizing the contribution of the M cells, and vice versa if we are interested in motion. Just to summarize the characteristics of the P cells and the M cells. So in terms of when are these cells active? And basically when we start with the P cells are the cone photoreceptors. Okay, so we have the rods and the cones. The rods, these are the M cells, the cones, these are the P cells. When are P cells active? P cells are active at a high luminance. So we need a certain level of minimum luminance to get these cells active. Okay, so if it is night, for example, it's dark outside, then we are typically seeing with our M cell system. This is why we cannot perceive colors, because the P cells are not active at that time. Okay, so we need a high luminance. They are very sensitive for high luminance contrasts. Okay, so the maximum luminance contrast that I can get is black and white. Okay, so luminance of best case 0 and a high luminance of around 100, 120 candela, so dependent on the screen that you are using. Okay, so high luminance contrast. Further, they are sensitive for color information. Okay, so we have the green, the blue, and the red photoreceptors with the corresponding wavelength that is perceived by these photoreceptors, and they are sensitive for high spatial resolution. Okay, and in the end, this also defines how we have to design a stimulus that activates the P cells. Okay, so we will see this later, how such a stimulus looks like. On the other side, we have the M cells. The M cells are connected to the rod photoreceptors, as I said. They are active at low luminance. Okay, so as I said, when it's dark outside, we do not have any light sources, then we are basically seeing with the M cells, with the rod photoreceptors that are not sensitive for colors. This is where everything appears grayish in the end. They are sensitive for low luminance contrasts. So just the opposite to the P cells. They are sensitive for stimulus speed. Okay, so that is important when it comes to the investigation of motion information, because these cells are speed sensitive and also later in the visual system. and they only provide a low spatial resolution. Okay, because we have larger receptive fields, we are merging more signals into one of these cells, so the spatial resolution is way lower when compared to the P cells. Okay, and this is the motion system. That is a system that is used for detecting motions. And that is later what we have to consider when designing our stimuli. And last but not least, one last information for that part. We have to consider that the rods and the cones, and here especially the cones that are color sensitive, are organized in a certain way in terms of color processing. Okay, so we have these receptive fields. It's indicated here with red, green, and blue, yellow. This is how the cones are connected. This is how the cones perceive colors. Okay, so they are active by red-green contrast and blue-yellow contrast. At least this is the maximum activation that we can get, because this is how it is processed on the retinal level. Okay, so again, if we want to have a visual stimulus that maximally activates the color system, then we can go with a red-green stimulus or with a blue-yellow stimulus. Okay, so any other colors would work as well. However, this would negatively affect, for example, the signal-to-noise ratio. Okay, so we would get less signal because this is how it is processed on the retinal level. And these are basically the structural and functional characteristics that then form the basis for us to design the stimuli to test the visual system. This is when we talk about visual evoked potentials. Okay, so we present a visual stimulus and we are getting an evoked response that we can analyze. And we have to consider what are the characteristics of the visual system. And that is also something that some years ago, there was a bit confusion, especially in the field of sports. I will come later back to that, because these two systems were mixed all the time. And it was always the question, okay, why do we see no differences? Or why do we see difference in some studies and not in the other studies? Because they all mixed up the different types of stimulation. But we will see that later. So just a quick overview of what happens on the retinal level. Okay, so I will not go further into detail. However, just to make clear, let's say, what are the structural and functional characteristics that drive the selection of the visual stimuli. So let's go a step further and talk about, okay, what stimuli do we need? What stimuli do we need to later get a visual evoked potential? And what we ended up with is basically this part here we discussed, okay, so the contrast and color system with the P cells, the characteristics, and the same for the motion system. So when we are doing visual evoked potential experiments, then we are going either on the one side, okay, so we are checking contrast, color, and we have to ensure that we maximize the activation of the P cell system while minimizing the activation of the M cell system, because otherwise we cannot differentiate and we would not know if there is, for example, a deficiency in one or the other system. And the same applies to the motion system as well, so to the M cells. When we are investigating motion, then we have to ensure that the contribution of the contrast and color system is minimized. Okay, so best case, there is no contribution. Of course, there is always some kind of overlap. It does not work perfectly. Nonetheless, we have to maximize the contribution of the system that we want to investigate and minimize the contribution of the other one. That is the ultimate objective. And this is how we design then the stimuli to investigate the visual system of interest, either the P cell system or the M cell system. So how do then the stimuli look like? Of course, there are hundreds of different stimuli in the literature that all have some specific characteristics. I will just present you two for the P cell system and one stimulus for the M cell system that have maybe the highest signal-to-noise ratios. So coming first to the P cell system. So what we said is that the P cell system are activated at a high luminance. We have high luminance contrast or color contrast because they are sensitive for colors, and we have a high spatial resolution, or the cells are active at a high spatial resolution. And this is reflected, for example, in these so-called chessboard stimuli. Okay, so these are pattern reversal chessboard stimuli. Okay, so reversal just means you have this chessboard with, on the left side, black and white, and this changes from black, white to white, black, back and forth. Okay, so that is meant by pattern reversal. Why are we using this stimuli? Well, we can have a high luminance. Okay, so high luminance, for example, 60 candela per square meter. Okay, so depending on the screen that you are using, the luminance could be even higher. We have a very high contrast. Okay, so contrast that you can achieve, for example, with a CRT screen is around 98%, okay, which is quite good. With OLED screens, it could be even higher. And we have a very high spatial frequency, okay, because we have these sharp edges between white and black. And considering that, we are basically fulfilling all the criteria on the right. So what makes the P cells get active? And on the other side, we are minimizing the contribution of the M cells, okay, because there is no motion in the stimulus. The luminance is very high. We do not have low spatial frequencies, okay, so we have an activation of the P cells while minimizing the contribution of the M cells. We can do the same for the color system. Okay, so as I said, we have the red, green, and blue, yellow color opponent cells. Okay, so I could also replace this with a red-green stimulus. Okay, so here I've used a blue-yellow. We have to ensure again that we have a high luminance. Again, it depends a bit on the screen that you are using. For our example, what we have used in our laboratory is around 40 candelas per square meter. We have a maximum color contrast in that case. Okay, so blue and yellow would be the same, red and green. Important here that we need an isoluminant stimulus, which means that the luminance of the yellow patches is the same as for the blue patches. Okay, because otherwise you're again, or you would mix up luminance contrast that we have on the left side, black and white is a luminance contrast, with a color contrast. Okay, so here we only want to have a color contrast, which means that the stimulus of the blue and the yellow must have the same luminance. Okay, so to not have any luminance contrast. We have the same high spatial resolution or spatial frequency, so these sharp edges in this chessboard. So we are again fulfilling all the criteria that we have for an activation of the P cells. Okay. So in sum that we can say, all right, this type of stimulus does activate the P cells maximally, let's say, for the luminance contrast on the left side, black and white, or the color contrast on the right side, blue-yellow or red-green, doesn't matter, while at the same time minimizing the contribution of the M cells. Okay, so the motion system. There is no motion, not low luminance, and so on and so forth. Okay, so that is a type of stimulus that you can use for that. Okay, there are of course others in the literature. Gratings, something like that. Gabor gratings, for example, are very often used. Nonetheless, in our experiments, we have typically used these stimuli, and the signal-to-noise ratio is quite high. Okay, so the current recommendations from the ISCEV are around 50 stimuli. Of that is sufficient to have a valid visual evoke potential. Okay, so it's a very fast experiment, takes around maximum a minute or something like that. So it's very time efficient. Let's go a step further and have a look at the M cell system. So coming to the motion part. For the motion, again, maybe just to remind you what are the characteristics of the motion system, the M cell system. So here we have the rod, the photoreceptors. They are active at low luminance. Okay, so something that we have to consider when designing this stimulus. They are active at low luminance contrasts. Okay, so we have to avoid, for example, this black and white. Okay, so we need lower contrast. They are sensitive for stimulus speed. So there must be some kind of motion in the stimulus, and they provide only low spatial resolution. So we have to avoid these sharp edges, okay, because otherwise we would have an activation of the P cells, what we do not want. So how does the stimulus look like? Basically, it looks like what you see on the top left. Okay, so that is the stimulus. At the moment, it's not moving, obviously, but you have these circles, and these circles are then in the motion either expanding or they are contracting. Okay, so you have some kind of radial motion. The luminance is very low. Okay, so typically it is around 17 candela per square meter. That is what is recommended in the literature, so that the P cells do not get active because they need a higher luminance. The contrast is very low. Remember, for the P cells, we were close to 100%, okay, 98% approximately. Here we only have 10% Michelson contrast. Okay, so you also see this in the picture that we have different gray shadings, and the contrast between the light gray and the dark gray is 10%. Okay, so again, that the P cells are not getting active. We have a low spatial resolution. Okay, so we do not have these sharp edges, but we have some kind of fading between the light gray and the dark gray. Okay, so we have a smoother transition between the different colors or the different gray shadings. It's not a color. Further, we exclude here the central 5 degrees. Okay, so you can see that in the middle, these 5 degrees, it's just a stationary gray circle. Because if we have a look at the distribution of the M cells, we said that before, that in the central 5 degrees, there are not many M cells. There we have the P cells. Okay, so in the central part of the retina, in the fovea. So we are just blocking this and saying, all right, there is no motion, there is nothing, just a gray circle, to again avoid activation of the P cells. While more in the periphery, where we have the M cells, we still have the motion, we still have the circles that are moving. Okay, so again, contributing to a maximum activation of the M cells and a minimum activation of the P cells. And last but not least, we are activating quite a wide visual field. Okay, so in our experiment with 50 centimeters of distance between the person or the person's eyes and the screen, we have around 44 and 30, 33 degrees of the visual field that is active. And again, if you have a look at the distribution of the M cells, dependent on the eccentricity, then we see that the peak that is around 20 degrees of eccentricity is well covered here. Okay, so just to improve the activation of the M cells. Question? Yeah.
Is there any preference for the vertical or the horizontal orientation when it comes to the rod cells and like the M cells connected to the rods?
Basically, this is the distribution for the horizontal part. Okay, so this is horizontal eccentricity. And typically for the screens or the typical screens that you're using, you have more expansion on the horizontal when compared to the vertical side. Okay, so this is why for the horizontal, it is typically a bit larger when compared to the vertical. Okay, nonetheless, since we are covering these 20 degrees, that is fine. So we could also reduce it, let's say, to 35 degrees times 25 degrees. Okay, so the signal to noise ratio would be a bit lower, but still, since we have the peak, that is what we want in the end. There we have the highest activation. Okay, but what is displayed here? This is just the horizontal side.
Because also from the evolutionary perspective, I guess it makes more sense to screen horizontally the environment where you're in.
Yeah, right. The tiger was typically coming from the left or from the right, not from the top. Yes, that's true. So to be honest, I would have to check if the distribution is the same also for the vertical axis. I'm not 100% sure, but as you said, from an evolutionary perspective, that would make sense that we see it more on the horizontal side in the periphery. Okay, and this is typically what we are then also considering in the stimulation. All right. So this type of stimulus then specifically activates the M cells, while at the same time minimizing the contribution of the P cells. And that is what we want, so that in the end we have, or based on these examples, we have 3 stimuli that are maybe best suited to investigate these 3 visual systems. Okay, so we have the color contrast system, black-white, chessboard pattern reversal could be a classic stimulus for that, sharp edges, white and black, a lot of contrast. We have the blue-yellow or the red-green for the color system. Okay, so dependent on what you want to investigate. I will show you later some examples because we did this, for example, with athletes. And these motion stimuli where you have these expanding and contracting circles for the motion stimulation. There is actually a lot of research that also tried to investigate, okay, what is the best stimulus, especially for the motion? And they had some kind of spiral motion, translational motion, and many, many different stimuli. And that was in the end the one that has the highest response. Okay, so in terms of amplitude of the visually evoked potential, that was the one with the highest response and the highest signal to noise ratio. Okay, so that is also why we ended up with this specific type of stimulus, because as I said, the visual system is one of the best investigated systems in the brain that we have. And that is the stimulus that they came up with. So how does it look like then when we are doing a visually evoked potential experiment? And I will just show you a visually evoked potential right now that you have an idea how that looks like later on. Basically, it then looks like this. Okay, so I've excluded here the color contrast stimulus. I will show you an example later on. But we see on the left, this is a classic pattern reversal, black-white stimulus. And you see underneath the visual evoked potential. Okay, so we have 2, sometimes 3 potentials that we investigate. Okay, so we have the first negative potential around 75 milliseconds, so the N75. Then we have the strongest, or typically the strongest potential, the P100, so positive potential after 100 milliseconds after stimulation. And then sometimes, or in around, I would say 50% of the participants, you will also see the so-called N145, so a negative potential around 145 milliseconds after the stimulation. Okay, but here, as I said, in around 50% of the participants, you do not see it all the time. So typically we are investigating the first 2 of these potentials. I will show you in a minute what these potentials mean. For the motion onset, so for these radial circles that are moving, the same procedure, we have a visual evoked potential here. Okay, so you see the temporal profile underneath the stimulus. Here we have, basically we have 2 potentials. Typically we are investigating the second one, so this large N2 potential, or N200. Okay, so dependent on the study, it is sometimes termed a bit differently. So it's a negative potential that occurs approximately 200 milliseconds after the stimulus onset. And if you have a look at the very bottom on the cortical mappings, you see that the pattern reversal visually evoked potential, so for the luminance contrast, and the same also applies for red-green and blue-yellow. This is located primarily in the primary visual cortex. Okay, so V1. While for the motion onset visually evoked potential, we have it primarily located in area MT. Okay, so MT stands for the mid-temporal area, and in there we have this region that is specifically associated with motion information processing. And that was also this confusion that we had a long time in the field of sport and exercise science, because I said that the visual system is maybe the best investigated sensory system that we have. However, in the field of sport and exercise science, for a very long time, there was not that much of research. And if there was research, it was typically a pattern reversal stimulus, because this is a classic stimulus that you also use in clinical practice. Okay, so you need one electrode here, and then you're stimulating, and you will see right away if there is, for example, a delay in the potential, is there a reduction in the amplitude or something like that. And they did the same with athletes. And the results were very, very heterogeneous, because in some studies there was a difference, in some studies there was not. So it was a lot of confusion if there is an adaptation in the visual system. However, it seemed that it is maybe more appropriate to investigate motion, because in most sports, athletes depend on the perception of motion and not of contrast or colors. Okay, so the badminton player typically does not care if the shuttle is yellow or green or blue. It's more about identifying the speed of the shuttle, the trajectory, the direction, and things. Okay, and this is also what we observed in our studies. I will show you that later on, that there are no differences at all in the pattern reversal visual evoked potential, while there are massive differences in the motion onset visual evoked potential, because we have two completely different systems that we are addressing with these stimuli. Okay, so bottom line is just that we have to think about, okay, what stimulus are we using? What visual system do we want to investigate to avoid this confusion that very often happened in research? Good. But maybe just to quickly explain what these different potentials mean. So for the contrast visually evoked potential, the N75 and the P100, there is still some discussion in the literature about that. But in the end, both are associated with visual perception. Okay, so it is the initial perception of contrast information or color information, dependent on what stimulus you use, what we have just discussed. While the N145 is more related to visual processing. Although, as I said, sometimes that is not identifiable. Okay, so around 50% of the participants, you see that, and 50% not. But if it comes to the visual perception, then the N75 and the P100, these are the potentials of interest. Okay, and for example, if you have patients with a macular degeneration where the central part of the visual system is degenerating, then you will see the characteristic delay in these potentials. Okay, so the P100 has a way longer latency, and you also see a drop in the responsiveness, so in the amplitude of this potential. Question? Yeah.
Yeah. More about the evoked potentials that you've got here. I'm not used to this Y scale unit. Like, why is it like microvolt per square meter?
Because we use current source density here. So we use current source density transformation because these are quite focal potentials. So we wanted to have some kind of spatial high pass filter. So we use the CSD transformation, and then accordingly you're getting a different unit. So it's not microvolt, but per square meter.
The transformation we can do universals if I've seen it in results.
Yeah.
The reason was what I like just like to keep it comparable to the literature, I guess, like, so you need this because,
well, we want to identify also the location of these visual evoked potentials. So these visual evoked potentials are quite focal. Okay, so they are quite specific. So we were using this spatial high pass filter to have a better localization. Okay, I have later a study where they are explaining the CSD when compared to other referencing methods. Okay, so just to get a better localization of your potential of interest, to have less blurring, let's say. Okay.
So
it's not one electrode. It is like all electrodes covering the V1. But you have, by this filter, you have like this very large amplitudes.
It is still the electrode level. Okay, so but it is just a transformation based on nearest neighbor and spline interpolation. Okay, so it's just the CSD, the current source density transformation, that just considers, or it's a recalculation of this electrode position based also on the activity of the nearest neighbor electrodes. Okay, so that you can better identify, okay, where is the signal coming from? Because if you have a signal underneath one electrode, it will spread also to the other electrodes. Okay, and then to make it more focal, okay, to better identify the source of this potential, you're using the current source density.
Probably just follow-up question.
Mhm.
If you would be plotting here the same without source transformation, like what would be the difference in terms of like the ratio between, let's say, N75 and P100?
You mean in terms of amplitude?
Yeah.
It would look more or less the same. Okay, because, or what would be different would be especially the electrodes around it. Okay, so here we are going with OZ because OZ is the best representative of the primary visual cortex. And if I would plot also O1 and O2, then you would have a stronger attenuation of the signal when compared, for example, to an average reference. Okay, so here it's just more focal. I can show you later mappings. I have it in some presentation where it's directly compared a CSD mapping versus an average reference mapping. Okay, so we can have a look later on. I think it's in the second presentation. Good. So contrast VEP, especially N75, P100, these are the potentials of interest for the motion visually evoked potential. As I said, we have in the end two potential that we can identify. This N1, I put this in parentheses because typically we are not investigating that. It is some kind of initial activation of area MT, but it is unspecific. Okay, so maybe you can imagine it in a way that the visual system or area MT recognizes, all right, there is something, there is some kind of stimulation in the environment, but at that moment in time, the system does not, let's say, know yet what is it, what type of motion is it, what speed is it, and so on and so forth. Okay, it's just some kind of initial activation. You have the same in motor areas as well. What we are interested in is this N2 potential, because this is the motion-specific perception and the motion-specific processing. Okay, so there are also some studies, for example, with TMS, where you interfere with this N2 potential. If you're doing that, your reaction times are delayed, something like that. Okay, so indicating that this is about the processing of the visual motion information. What we are then interested in, what we are typically analyzing when we are comparing groups or comparing time points, comparing conditions, is that we are going on the amplitude. So basically the neural activation or the investment of resources, depends on how you would like to interpret it. And also the latency. Okay, so the latency, the perception / processing speed. Okay, so dependent on the potential you are interested in, it's either perception or processing, and the time it takes for the visual system to run through these processing or perception steps. Okay, so that are the information that we later get out of the data. All right. So far for the different types of stimuli and what we get in the end. So maybe we can have a quick look at the EEG and the experimental setups. So I think for the EEG part, I do not need to go into too much detail. Typically, when we are doing these experiments, we are using a 64-channel system where we have the different areas of the brain covered. And especially when it comes to the visual parts, I will just go through this. We are interested here in what is at the very bottom. Okay, so we have, of course, the primary visual cortex. This is electrode position OZ. Okay, so that one. The visual motion sensitive area MT is best represented by the electrode positions P07, P7, P5, and the corresponding electrodes on the right hemisphere. Okay, so there are studies that map basically the electrode positions to the corresponding cortical areas. So there is a study of Köstler, I think 2009, some years ago, but he did this very nicely where he projected the electrodes to the parts of the cortical surface. And if you're looking in fMRI studies, for example, where the area MT is located, then these are the electrodes corresponding to that. Dependent on the experimental protocol that we have, for example, if we are combining a visually evoked potential with some kind of motor activity, a reaction test or something like that, then we are also covering some of the motor areas or the somatosensory areas that are here indicated in green and blue. But again, that depends a bit on the experimental protocol that we are using. What is maybe more important in terms of experimental setup is the standardization that we need, because visually evoked potentials are very sensitive to many different aspects, many different things that may change in our experimental setup. So I tried to summarize the most important parts on the next slide. So when we are doing visually evoked potentials with a contrast stimulus, okay, and that applies to both a luminance contrast and a color contrast stimulus. So this type of stimulus depends on many, many different parameters. So it depends on the luminance intensity, the luminance contrast, obviously, because as we discussed, the P cells are very sensitive to high luminance, to high contrast. So if there is a variation, okay, for example, it could also be due to ambient light that is changing. If it changes the contrast of your screen, if there are reflections or something like that, then it will change your visual evoked potential. Okay, so this is why when we are doing these types of experiments, whenever possible, we are using a room without windows, or we will just cover the windows completely in black, that we can standardize the ambient lighting conditions. Also, the check size does make a difference. Okay, so if you have smaller checks or larger checks, okay, these white and black patches will change the amplitude and latency. It also makes a difference, for example, if you're using CRT screens, LCD screens, OLED screens. Okay, so you will obviously not see that, but your visually evoked potential will be different. Okay, so that is also something to consider. And you have to basically consider that when you are also comparing your results to other studies, because that can have an influence. I already said the ambient lighting conditions can have an influence. Okay, so if it is very bright, it will lower the contrast that you have, and also the distance of the screen. Okay, so between the eyes and the screen. So what we are measuring typically is the distance between the eyes and the screen, so not the person, that you have exactly the same distance, because otherwise you have a different size of visual field that is stimulated, and again, this can make a difference in the end, an amplitude and latency of your potential.
What's the distance that you
So we have calculated it for the pattern reversal, 750 millimeters. Okay, so depending on our check size with the visual angle, it was 750 millimeters. And for the motion, we were reducing this to 500 millimeters just to have a wider visual field. It would still work with 750 millimeters. Okay, so it would then be not 44 times 33 degrees. It would be then around, I don't know, 38 to 30 degrees, something like that. Okay, so we just said, okay, we want to have it a bit larger. So we moved the screen closer. However, there are obviously limitations, because at a certain point you can count the pixels and then it doesn't make sense any longer. Okay, so we were using 750 and 500. Yeah. So same for the motion onset VEPs. Yeah, 500 millimeters is quite close. For the motion onset, what has an influence? Obviously, again, the luminance intensity. Okay, so this is also why before every experiment, we are checking the luminance. Okay, so we have a light sensor and just ensuring that we have, for example, the 17 candela that we want. The motion velocity has a huge influence. Okay, so I will also show this later in some studies. So dependent on the speed of these circles moving, you will have a different response. So the higher the velocity of these moving circles, the lower is the latency, so the faster it is processed in the brain, and also the higher is the amplitude. Okay, so that is something that we have to consider as well. The stimulus duration, okay, so how long do you have this motion of expansion and contraction? Is it 200 milliseconds, 400 milliseconds, a second, or something like that? And also the stimulus direction. Okay, so it makes a difference if it is expanding or contracting. So these are all parameters that we should consider when setting up an experiment. And especially we have to standardize them. Okay, so we have to ensure that the conditions in here are the same for all participants. Yes.
Can you elaborate on the differences discovered when the circles are expanding versus shrinking? What kind of differences would you expect to observe in the potential?
We have not differentiated between them in our experiments. However, why you are doing this, or typically you are expanding and contracting in a randomized order. Okay, so you're typically randomizing the expansion or contraction that the participants first do not know in what direction it does go. And further, or the major reason behind that is, again, signal to noise ratio. Because if you're only expanding or only contracting, then at a certain point, the cells get desensitized, let's say. So their response will get lower and lower after a while. Okay, so this is why we are expanding and contracting in a randomized order. Okay, so just to increase the signal that you generate with this motion stimulation.
But you never looked into differences dependent on the direction.
Not in our studies. Okay, so we could do that, but in the end, what we want is the highest possible signal to noise ratio. So we are randomizing the orders. Okay, and if we would split it, typically we are designing our experiments that the signal to noise ratio is sufficient for the number of stimuli that we use. If we would now split it in half, let's say, then I would not be sure if the signal to noise ratio is still sufficient. Okay, because then 100 would become 50 and 50, and then it gets a bit tricky.
Can I also ask you to repeat again what you said before regarding the speed? So signal to noise ratio would be the largest if speed is faster, or what would be the optimal speed of shrinking or expanding?
So we have tried 3 different speeds. Okay, so the speed here is operationalized in hertz. Okay, so cycles of gray shadings per second. And we have used 5 hertz, 10 hertz, and 20 hertz. Okay, and you see that from 5 to 20 hertz, you have, with a faster stimulation, a larger amplitude in your signal and a lower latency in your signal. Okay.
It doesn't affect the signal to noise ratio, it just affects the amplitude and the latency.
Basically, or we have to assume that it does affect the signal to noise ratio because the signal is larger at higher speeds. Okay, so assuming that the noise is constant, what I would do, I do not see a reason why to assume that the noise is different. Then the signal would be stronger if you have a faster stimulation. What the upper limit is, we don't know. We don't know if, for example, with 60 hertz, I would assume we would not even be able to see any motion because it's too fast. Okay, so we have not tested the upper limit for that. Okay, nonetheless, we see these dependencies.
Has there been any mapping of like the several more hertz? And like, because then I would assume it comes down to like the reversed the exponential function. So the highest signal to noise ratio at the other way around actually. It would be exponential then.
You mean the signal to noise ratio?
Yeah, it's compared to the speed of the hertz. Yeah.
To be honest, I don't think so, because at a certain point you would not be able to identify any signal, I think, because at a certain point of stimulation frequency, you're also running into problems with the refresh rate of the screen. So I would expect that at a certain point it becomes more of an inverted U shape. So as I said, we have not tested that. We have not tested, for example, with 50 or 60 hertz. I've tested it just for fun, let's say, but not in an experiment. And at 50 hertz, I was not able to see anything. It was just some kind of blurry, whatever. It was not a clear motion. So I would expect that you do not have a high signal to noise ratio there.
I think that for steady state applications, which are not explosions, they use around 40 hertz to stimulate the primary region. So, but it's not directly related.
Yeah. Yes, so for steady state, you would then have higher frequencies. And yeah, for the motion, we have not tested that, to be honest. It's just an assumption, but at a certain point, it's very hard to identify motion on the screen if the frequency is extremely high. So, yeah. Yeah.
We have another question online. Can you apply visual potentials research on real life situations?
Yes, we can. So, okay, then.
You can just repeat the question for online.
Yes, of course.
Yeah.
Okay, so yes, we can, of course. Okay, then I will start with the experiment now. Typically, it was planned later, but we did an
Ask the question.
experiment.
Hello,
with,
can I ask the question?
Professional badminton players. So that was, I don't know, 7 years ago, where we started to identify the differences in the brain between badminton players and non-athletes in reaction tasks. Because if you measure the reaction time, not surprisingly, badminton players are faster than non-athletes. Obviously, because they are performing in a very challenging environment, they are getting faster. And we wanted to understand what are the differences in the brain. So we did these analyses with the visually evoked potentials, with these stimuli that you can see on the screen. And we identified that athletes were faster in the visual system than non-athletes, but only in the motion system and not in the contrast system. So the contrast system was absolutely identical, while in the motion system, the athletes were way faster. Okay, so I think in absolute numbers, it was around 12 or 50 milliseconds. Does not sound that much, but in badminton, remember maximum ball speed, 500 kilometers per hour. So 50 milliseconds is quite a lot. So this is what we identified initially. And then we thought about, okay, how can we train that? Because we also investigated the motion system. Okay, so movement preparation, movement execution. And there was no difference between athletes and non-athletes in terms of the motion planning. So we said, all right, the visually evoked potential is somehow related to their better reaction performance. And with regression analysis, it was an R of around 0.9, so quite high. So the faster or the lower the latency of this potential, especially this N2 that you see on the right, the faster was also their reaction time. So we translated this into a training study where we used shutter glasses to train their visual system. And we did, again, exactly this type of analysis, and we observed that later on, their reaction time after the training was significantly faster than it was before, and changes in reaction time were again directly related to changes in latency of this N2 potential. Okay, so indicating that the performance gains in reaction time were related or were attributable to some kind of functional changes in the visual motion system. Okay, so the explained variance here, if I remember correctly, was 64%, okay, which is already quite a lot. Okay, so 2/3 of the training gains were attributable to the visual system as investigated with the visually evoked potentials. So that is maybe some kind of application that you may think of how to use it. Apart from that, it is very often used, as I said, in the clinical settings. Okay, so to identify deficiencies in the visual pathway or something like that, that could be another type of application. But for my field, for the field of sports, this is how we have used it. Okay, starting with the comparisons, athletes, non-athletes, and ending up with the training application, and then translating this into training recommendation that are now with the coaches of the Badminton Federation, and they are integrating this into their coaches' education. So there is some kind of transfer, I would say. All right. Further questions?
I think it would be really interesting to apply it if you have like this kind of a data on professional athletes in case any one of them gets injured, if how to basically help them further on if we can speed up their recovery. I don't think there's anything in this like similarly applied yet, or is it?
So speeding up their recovery by using what?
Just like figuring out if you can, like, it's kind of a thing into helping them recover.
You mean these
faster.
shutter glasses? You mean these shutter glasses, or?
Yeah.
I'm not sure if it would help them recover. Nonetheless, you could use it, for example, to reduce the performance loss, because if they are not able to perform on the court and they are not exposed to this challenging environment, then of course you may also lose some of your abilities. So you may use that during their rehabilitation or something like that, not on the badminton court, but with other tasks that you can do. But we have not tested that. So luckily, the badminton players are not that often injured, so the sample size will be very low. But yeah, I get the point. So, and I would say, yes, that could be something that may work. Okay, because in the end, or why we are doing that is, because if you're playing badminton at a certain point on a high level, you cannot make the game faster. Okay, so even from a physics perspective, the ball cannot get any faster. If you want adaptations, you have to challenge based on the environment. You have to make the environment harder. This is what we are doing with the shutter glasses. Okay, so it's the same as with a marathon runner. You would not tell a marathon runner, if you want to run the marathon faster, go more running. Okay, so this is not how it works. So you think about, okay, how can you train? High intensity training, high volume training, all these different things. And here we have to do the same for the brain. That is the intention. Okay, because otherwise you would just level off at a certain point. Okay, and you have to think, okay, how can we train the brain? All right. So bottom line here, when we are considering all these different things, when we are standardizing, then we have quite a good signal to noise ratio. Okay, so as I said, from the ISCEV, so the Organization for Visual Research, I forgot exactly the name, what it was, but they are recommending for the contrast VEP 50 at least. And with that, the signal to noise ratio should be sufficient. Unfortunately, there are no recommendations for this motion stimulus. Typically, what we are using is around 150 to 200 stimuli just to be on the safe side. Okay, so with that, the signal to noise ratio is sufficient. With the contrast, it is easier. I mean, you need less stimuli, and it is also faster in conducting the experiment. All right. It's already 10, so I still have some slides, but should we continue or should I get break?
You want to break? I don't want to break.
No. I can present some of the results maybe then at the beginning of the next session before we come to the analysis part. Okay, so just to see what these visually evoked potentials depend on, okay, in terms of stimulation speed, and also maybe the phase of the signal, something like that. I've prepared a few slides for this, and then we can go to the analysis. Make sense?
Is there another question in the chat? I mean, there was another question in the chat. I just didn't get if you managed to answer it, or you were presenting or not. There's a question, or
I do not have the chat open here, so I cannot see that.
so it's the difference between VRP and VEP in terms of components.
Well, that's a mean question to ask.
Okay, so we have not investigated the Blink VEPs, so I would have to check what the components there are. But this is also why, for example, if there are blinks during the data acquisition, we are not, or we are never correcting these blinks. We are always excluding the participant, the segments, because otherwise we would not know, okay, what is related maybe to a blink or just missing the visual stimulation and what is a real visual stimulation. But we have not compared that. So we have not tested blink VEPs.
It's not let's say field of focus, but have you ever looked at any models of visual system or like visual motor system based on the visual stimuli and then depend on the motor output performance? Modeling in sense of thinking, I don't know, population neuronal models like exponential integrated environments or the models like I don't know, some common model or something like this in terms of getting some simulated data which you can test your experiment?
No, we did not. So typically we are then relating this to behavioral outcomes, just like reaction time, things like that. So we are typically measuring on these types of experiments. We have the motion sensitive areas for the visual perception and processing part, the motor areas, so especially BA6, and then some kind of behavioral outcome in addition to EMG onset data. Okay, so to see if there are relations between the motor components, the visual components, and the behavioral output. but we have not modeled that together.
Good. That's a break.
Yeah.
Okay.
That's fine.
Say to the others that we will be back in 15 minutes.
All right. So for the online audience, we will have a short break and then we'll be back in around 15 minutes and continue with the presentation. All right. Welcome back. So let's continue. We were not finished with the presentation. So let's do that now, and then we will go to some real data, and I can show you some of the results that we got from our last studies, basically. So, okay, I do not share the screen. Okay, now I can share. Screen 2. All right, now it's shared, right? Okay, good. This is where we stopped prior to the break. So we ended with this information on the signal to noise ratio, just one example, because I've just calculated this for a single participant. So this was with a contrast pattern reversal visual evoked potential. So you see on the top left the stimulus, so this black-white checkerboard, basically the electrode position here was OZ, corresponding to the primary visual cortex. Overall, we had, after artifact rejection and things, 193 potentials. And you can see, if you're looking on the right, so top row on the right, that we have here a clear visually evoked potential, a participant where we also see all three potentials, so a clear N75, a clear P100, and a clear 145. Then I just try to get the same visually evoked potential with different numbers of trials, and you can see that the signal to noise ratio is actually quite high. So obviously with one trial you cannot see anything, with 10 trials not really, but everything above 50 trials, and this is also the recommendation of the ISCEV, above 50 trials you can clearly see the visually evoked potential here. So basically that is the one for the 50 trials. Okay, so that is the P100 in the end, which is already at the point where it should be. And then there is not that much of a change to 100 trials. Okay, so here with 50, we already have quite a good number to get a valid estimate of the visually evoked potential in the end. Okay, so as I said, this is the ISCEV recommendation. Unfortunately, there is none for the motion onset visually evoked potentials. So what we figured out is that it should be around 100 or higher. Okay, so typically you then get quite a good visually evoked potential also for the motion onset VEP, but officially in the literature I did not find any recommendation from this ISCEV board. Good. Then what we have not discussed yet, and this is then also the last part of this presentation, some results that we figured out in some of the studies that we have conducted over the last years. And what we were interested in, so obviously we were interested in the visually evoked potential. We were investigating the amplitude most of the time. Frequency is typically not that much of interest. Instead of, we are having basically continuous visually evoked potentials at way higher frequencies. But I will also present you just one study investigating the phase and how the phase of the signal affects the visually evoked potential. So let's have a look at the characteristics of the contrast and the motion VEPs. And I would like to start with one study that I've mentioned already sometimes before on contrast VEPs, because it has initially been developed in the clinical field. So it's a classic clinical measurement, typically with one electrode on OZ for the primary visual cortex, to identify certain deficiencies or whatever malfunction in the visual pathways. And that is one study. It's quite old, but the figure was nice. So I've copied the figure here in this presentation. And what they were doing here, they were doing a classic pattern reversal, visual evoked potential. Okay, so using also this kind of chessboard stimulus. You see the P100 that I have here highlighted with these red vertical bars. Basically, or what we have to consider is that here we have a positive down. Okay, so it appears like a negative potential, but it's positive down in this scaling. Okay, so don't be confused about that. On the left side, we have the normal subjects, and on the right side, we have the patients. Okay, so in that case, these were patients with a macular degeneration, so degeneration of the central parts of the retina, where we have the P cells, and the P cells that are responsible for receiving, processing this type of stimulus. And as we can see, we have a rightward shift of the latency. Okay, so indicating that the visual system activity for these patients is delayed. Okay, so it is significantly delayed, and also the amplitude is lower. So the responsiveness to the stimulus is lower when compared to the normal subjects. Okay, and that is how it is used, especially in a clinical context. Sometimes also motion onset visually evoked potentials are used, but typically it is this chessboard contrast visually evoked potential, because these, or the symptoms, let's say this delay in the latency, for example, is quite consistent. Okay, so you can easily identify if there is some kind of degeneration in the visual pathway. Okay, so if you want to go further into detail, then of course, and try to figure out at what level this deficiency does exist, already at the retinal level, or maybe the thalamic level, or whatever other measures, just like ERG, so electroretinography or things are needed. But still, you get a good idea of what is going wrong in the visual system, in that case, for patients with a macular degeneration. Maybe coming a bit more to what I said before, so the dependency of the visually evoked potentials dependent on, let's say, athletes when compared to non-athletes, or the stimulus speed and things like that. So I just would like to present you some of the studies that we have conducted to get an idea what affects the visually evoked potential. And the first study is again on the P cell system. So we conducted research with professional badminton players. So these were German badminton players, the highest level. So Olympic players, all were international players, and also all Olympic players. And we compared them just to normal participants who had no experience with badminton or table tennis or other visual motor demanding disciplines. And the results were like this. So maybe it looks a bit confusing, so let's go step by step. We had 3 different contrast stimuli. Okay, so we had this black-white one that you've seen on the slide before. Okay, so for luminance contrast, okay, black and white. And we also had the 2 color contrast that I've presented in the very beginning of this presentation. Okay, so we had the blue-yellow and we had the red-green. Okay, so these color opponent cells for these 2 colors. And we compared that between athletes and non-athletes. Okay, so the athletes are always here the black curve, or on the very right, the black curve, and the red one is for the non-athletes. And you can see, if we have a view at the top row where we have the black-white, the 2 lines are more or less identical. Okay, so the visually evoked potential, especially for the N75 or the P100, there is no difference at all between these 2 groups. Okay, so obviously it is not significant. And also in terms of absolute numbers, I think the difference in latency in the P100 was 0.1 milliseconds. Okay, so this is absolutely negligible. As expected, we have it in the back of our cortex, so the primary visual cortex. Also, when you're doing some kind of inverse localization, we just did this here with a quick Loretta view. It is in BA17, so corresponding to the primary visual cortex. We did then the same for the blue-yellow and the red-green color contrast. Also here, the differences were not significant. It seems a bit in the figure that the athletes have a higher amplitude when compared to the non-athletes. However, there was a lot of heterogeneity, especially in the amplitude. So when investigating this statistically, there were no differences between the two groups. And also in terms of latency, it is more or less identical. And the same also applies to the red-green contrast. Okay, so it doesn't matter what part of the primary visual cortex you stimulate, contrast or color, there are no differences between the two groups. Okay, so participating in badminton for, I don't know, I think on average it was 15 years or something like that, playing on the highest level, does not lead to any adaptations in this part of the visual system. And that was basically the stimulation that has been used in a lot of previous studies before, especially the one at the top row, so this black-white. That is what has typically been done. And there are some studies with differences and some with no differences. Sometimes it depends on the check size of the stimuli. No one had an idea why that could be the case. But here it seems to be that there is no adaptation. And it makes sense because badminton players typically do not need their contrast system, let's say. They do not care if a ball is blue or yellow or white or whatever. So we extended that and said, okay, maybe there is something in the motion system. Oh, sorry, question.
Do you have any idea why the blue, yellow, and red, green look so different? Like in terms of the shape of the waveform?
No. This is
weird. Huh?
I would not say that it is weird, because of course contrast and color information are processed differently. Okay, so if you are going to the luminance contrast, for luminance contrast, if you for example have white, then all three types of the cones are active. Okay, because if you have white light, then you have wavelength of all colors in there. So they are all either active or they are non-active. If we have a color contrast, then this is different. Okay, so then the contrast system is, let's say, switched on, while some parts of the cells are active. Okay, for example, the red and the green. And the way this signal is processed is differently also in the primary visual cortex. Okay, because you have different layers, for example, where the M cells and the P cells connect to the primary visual cortex. They are not all merging in the same layer. They are quite separated. So I'm not surprised that this visual evoked potential looks completely different. Why it looks exactly like that, I don't know. Okay, so I can tell you that we have the P100. The P100 you will find every time. Okay, and we also find it in here. The P100 is shifted to the right, which means that the processing takes longer. Okay, so the luminance contrast has a lower latency when compared to both color contrasts. But still, why the signal is exactly like that, I cannot tell you that. Okay, and I did not find that in the literature, to be honest. Okay, because there is a lot of black-white, red-green, blue-yellow. It is more limited, let's say. So I could not find an explanation for that.
So with your findings, then you said for the blue, yellow, and red, green, although for checking just the amplitudes, one would assume that there are significant differences between the amplitude of peak 100, right? You said due to the heterogeneity, no differences were found.
Yes, so we have not indicated here the standard deviation, but the standard deviation was very high. Okay, so it was way higher when compared, for example, to the classic black-white, let's say. Okay, so here this difference, it appears as a difference, but it is not statistically significant. Okay, so that is what we have to consider. And for us, the more important part was especially the latency, because we were interested in the speed of their visual system, because this is what we would assume to adapt somehow. But that was more or less identical in all three conditions. So there was no adaptation at all. But in the end, and this is what you can see in the mappings and also in these Loretta calculations, in the end, everything is in the primary visual cortex. Okay, so it doesn't matter if you have a luminance contrast, if you have a color contrast. In the end, we always end up with BA17, so V1. Okay, so that is what we did for the color and contrast system. but the hypothesis then was, okay, maybe we should find the adaptations in the motion system, because this is what counts for these types of athletes in the end. So we did another study, again, with the badminton players, the Olympic badminton players versus normal controls, blah, blah, as I said before. And here we have two different stimulation speeds. Okay, so you see in the top row, this is 5 Hertz, corresponding to a comparatively low speed of stimulation. Okay, so a slow motion of these stimuli. And then we have just doubled the speed by using a 10 Hertz stimulation. Okay, so in other studies, we also use 20 Hertz, but here we had 5 and 10. And we were interested then in the N2 potential. Okay, so I've highlighted that here. Basically, this is the N2 peak, around 200 milliseconds, a bit earlier. And again, we compared between the athletes and the non-athletes. And here we then see the differences between the two groups. Okay, so we have, again, the athletes indicated in black, and we have the non-athletes indicated in red, and we see that the red curve is shifted to the right. Okay, so indicating that the speed of the visual system in the athletes is higher when compared to the non-athletes. I see there is a question in the chat, so can they log in and unmute and ask the question? Yes, right. Work.
It worked yesterday.
Okay, so someone's raising the hand. Please go ahead with your question.
Hello, can I ask the question? Can you hear me? Can you hear me? Can you get me?
Yeah, you can tell us.
Okay, thank you for the good presentation. My question over here is, I just want to know, how did you handle the data, individual data? Let's say you have 10 participants or 20 participants. This component N2, N3, did you get what I'm trying to say? All these components that you are displaying, is it handled in the form of a continuous data or a categorical data? What type of data are you using in this? Let's say for the first participant, you have gotten N1, let's say N2, second participant N2, like in the athletes and non-athletes. So how did you, is it then data is in a numerical form or is in the categorical form? That's what I want to know. This component N1, N2.
Okay, so I did not get everything acoustically. Let's say I missed some part in the middle. So I think it was about something with data processing. Can you summarize that? I did not hear everything, to be honest.
Okay. The data obtained in EEG, let's say this component N2 component. Hello, can you hear me, this one?
Yeah,
for example, this N2 component, was it a continuous data or a categorical data? How will you record the data for the individual participant? Let's say, for instance,
we recorded, I think, in that experiment 200 trials, if I remember correctly, for this motion. Okay, so you have these circles moving, and then it was processed as event-related potentials. So basically, we segmented based on the stimulus onset, minus 40 milliseconds for the baseline, and then 400 milliseconds following the stimulation. And then we used an event-related potential approach. So we cleaned the data, and then we were averaging these 200 or whatever number of trials remained after the artifact rejection, and then got these potentials. Okay, so that is the grand average of all participants. Okay, so that is a grand average of, let's say, 20 athletes and 20 non-athletes. Okay, however, the latencies were individually defined for each person. Okay, so to later compare the latencies of the athletes and the non-athletes, we were not doing this based on that figure. Okay, but for every participant, we had an individual latency and amplitude of the N2, and then we put this into statistical analysis. This is just the illustration that comes out of it, that just, basically emphasizes this leftward shift for the athletes curve. However, we did this in the end based on absolute data. So we had this type of potential for every athlete and then identified individual amplitude and latency.
Maybe, sorry, maybe you are not, I'm clear the way you explain this one. I'm very clear with this one. What I just want to know is the data a continuous data or a categorical data? The data obtained, can we say it is a continuous data obtained from the individual participant, from the individual, let's say, athletes and non-athletes? These N2 components that you obtain, can we express it in terms of number or in terms of category? Did you get me?
And it's ERPs. So
yeah. Okay. Okay, I have no idea if I understood this correctly, but basically there are two groups that were compared. So we had the athlete group and the non-athlete group. So some kind of between group factor that we have here. Okay, so one between group factor with the two levels. And then we had the N2, either the N2 amplitude or the N2 latency as the dependent variable. Okay, so that may then depend on the group, athletes and non-athletes. I don't know if this answered the question, but
okay, for now. Okay.
All right. But for the bottom line here is basically that in contrast to the contrast, color and luminance contrast, we see here clear differences, especially in the latency, not in the amplitude. So the amplitude was more or less similar and statistically not significant between the two groups. However, we see a difference in the latency. So the visual motion sensitive area MT of the athletes is activated earlier when compared to the non-athletes. Okay, so in absolute numbers, we are talking here about 12 to 50 milliseconds. Again, it doesn't sound that much, but still 12 to 50 milliseconds with a high ball speed in badminton, that is quite a distance. Okay, so it's basically a distance like that. And it makes a difference if you see the ball already here or if you see it there. Okay, so it can make a difference if you're still able to defend the ball or not. So it seems that this is related to that type of training. Second, what we have seen here, and this is why I came to the conclusion that this N2 potential also depends on the speed of the stimulation. For the 10 Hertz stimulation, independent of the group, the latency is significantly lower when compared to the 5 Hertz stimulation. And this is what we have seen many, many times afterwards. So we did the same experiment with table tennis players. We did another experiment with badminton players. And we always see the same, that the faster you stimulate, the lower is the latency of this potential. Okay, so I've not included all the studies in here, but still there seems to be a clear relationship. As we have discussed before, I don't know if there is some kind of upper limit. Okay, so if 30, 40 or whatever Hertz is then the fastest, but we see here clearly this trend that with a faster stimulation, we also have a faster activation of the brain. So that is what we did for the perception part. Okay, so we were interested in, okay, the brain of the athletes, the brain of the non-athletes, is there a difference in terms of perception of contrast and motion information? However, we also wanted to know if this is somehow related then to their behavioral performance. And behavioral performance here means we wanted to know if this is related to reaction time. Because this is what has been known for decades now, that badminton players or table tennis or whoever are significantly faster in their reaction when compared to non-athletes. And obviously that makes sense because they are performing in a very demanding environment. So we wanted to know if this is also related to these types of visually evoked potentials. So we were doing that, and we were using basically a simple reaction time test where the athletes, in that case, just had to press a button later I will show you a study where we translated this more into a real life setting. But here we were doing this with a simple button press. Okay, so you see again this visually evoked potential. It looks a bit different because we had a longer interval for the event-related analysis. Okay, so we had half a second before and 1 second after the stimulation. We see again here clearly the N2. If you have a look at the lower part of the figure, again with the two colors, athletes in black, non-athletes in red, we have the same pattern of result, that the athletes curve is shifted to the left. We see again the localization and the motion sensitive area NT, so on both sides of the cortex. And we also see a correlation between the latency of the N2 and the EMG onset. So we were measuring the EMG onset for the index finger and also for the visual motor reaction time. This is what this VMRT stands for. Okay, so when they have actually pressed the button. That was only one parameter. We have investigated another parameter because everything that you see here is just a stimulus locked. Okay, so this is event-related activity that is locked to the stimulus. Okay, so the onset of this motion. We also did it the other way around, let's say, and we locked it to the event of motor activation. Okay, so to the EMG onset and also to the visual motor reaction time. Okay, because this N2 potential is not only locked to the stimulus, it is also locked to the response. And when we combine these two parameters, okay, so the stimulus locked and the response locked, then we are coming to a predictive quality of around, I think in this study it was 70%, and in the table tennis study it was up to 90%, depending on how homogeneous your group is. Okay, so the predictive quality of the EMG onset and the visual motor reaction time by the visual system of the brain is typically between 70 to 90%, which is quite a lot and indicates that the visual systems seem to be quite important for your visual motor reaction time. Okay, that was one of the reasons why we then followed up with a study that I've just mentioned in the first presentation, where we try to specifically train this motion system. Okay, because we have seen this strong relation between the motion system and the reaction time. Okay, so if you want to improve the reaction time, you should train the motion system. That was the rationale behind that. All right.
Should we comment on which electrodes now contributed to the ERP?
You mean in the time on the that was or the electrodes that we identified for REMT, so PO7, P5, and
the spatial pattern you chose?
No. That was based on this inverse localization study of, I think it was Kössler, the name, if I pronounced that correctly, where he projected each electrode to a certain area in the brain. Okay, and then we just compare that with the fMRI studies for the motion sensitive area MT and the corresponding Broadband areas, because this is way more precise than an EEG can ever be. So we identified these electrodes, used them, and since it was on both sides, we just merged it together. Okay, because okay, and then we came up with P5, P7, PO7, and the corresponding electrodes on the right hemisphere.
Okay.
All right. So that was a study for the reaction then, so not purely the perception part, but also the translation into some kind of behavior, although it was a simple reaction time in that case. However, and I think this was also one of the studies that came, one of the questions that came up in the first presentation. Can this be somehow used in a more realistic setting? Because here we are still in a lab setting, obviously. You're sitting in front of a computer screen, which is not really ecologically valid. Okay, this is also always the challenge to convince the players and the coaches to do something like that, because the first argument is, why should we sit in front of a computer screen? We perform on the court. So we tried to translate this into a more applied environment, not with badminton, because badminton is a bit too dynamic for EEG, but we were doing this with table tennis athletes. And in this study, and On the left, you see the experimental setup. The table tennis players were playing against a ball machine, basically. So we covered the ball machine completely in black, that the players were not able to anticipate when the ball was put out. Okay, so it was still some kind of simple reaction task. They were not able to anticipate that. Okay, so we also used some kind of background noise and auditory noise that they were not able to anticipate based on the sound of the ball machine. Okay, so it was quite annoying, but still, no one was able to anticipate that. So it worked in the end. So we had this ball machine. In front of the ball machine, we just had the light barrier that indicated, okay, now the ball is put out. We had microphones placed on the table that were indicating the ball plate contact, let's say, as well as the ball racket contact. Okay, so as some kind of response. And then we did the same as before. So we tried to identify the motion onset visually evoked potentials, because we have the motion onset here, not the stimuli expanding and contracting, but here we just had a ball that was put out by the ball machine, but still it was moving, obviously. And what we get, you see on the top right, so in this column D. And again, we see a potential that looks more or less like the N2 that we have identified before. And in addition to that experiment, also every athlete did the experiment on the computer. Okay, so on the computer screen, what you've seen before. And then we correlated the N2 of the computer with the N2 of this table tennis task. And the correlation was somewhere in the range between 0.7 to 0.8. So it was quite high, which then supported the conclusion that what we are measuring there is actually the N2 potential. And also the location of the potential, there was no space to put this in here, but also the location of the potential was again in visual motion sensitive area NT. So we said, all right, this type of cortical activity can also be measured in at least a more ecologically valid setting. Okay, so if you're a table tennis player, then you would still say, yeah, it's different if you play against a ball machine when compared to a real human. I would fully agree, but still, maybe we are at least a bit closer to a real sport environment in that case. So that seemed to be possible. And also on the second and on the third line, you see clear potentials. Here, again, response locked. Okay, so here we have locked it to the ball plate contact, let's say, and the ball racket contact. And again, we see these potentials. So again, this is the N2, that is stimulus locked and response locked. Okay, what we have seen in the lab experiment seems to transfer also to the more, let's say, field experiment. Okay, at least a bit closer to the real world.
Sorry, so
yes,
that's again connected to the motion sensitive area, or
yes,
did you look at the central level more specifically for the response lock?
No, this is just for the visual motion sensitive area MT. Okay, so we were assuming that we would find the same visual evoked potential as in the lab experiment. So we were using the same electrodes again, so the same setup, and run the same type of analysis. Okay, so that is again this area MT, and that is the potential that we got. Okay, and then we correlated that and figured out, all right, there seemed to be quite a strong relation between the lab test and the field test. Okay, what I've not said, what the athletes had as well was some kind of mechanical switch that was placed in front of them. So they had to put their racket on the switch. When the ball came out, they had to defend the ball. So we also had the information on the reaction time here. So we had the reaction time in the lab experiment, pressing a button, and the reaction time in the field experiment, moving the racket, because the ball was very fast. And we correlated that as well. And there was also a correlation for the reaction time. So the athletes who reacted fast in the lab experiment, button press, were also the athletes who reacted fast in the field experiment, so moving the racket. And the fastest athlete is now preparing for Paris 2024. So I don't know if this is a coincidence, but no, of course it's not. It's not evidence, but still. So there was one athlete who was really way faster than everyone else. And these were junior players. So they were 12, 13 years of age. And she will next year then play in Paris. So she's very good, not only in reacting, also in other things.
Really interesting. I used to play table tennis for 10 years. I don't remember having this kind of machines. In my times, the machines were just like positioned. So you basically could train with the machine, but always constantly in a constant direction. So wherever you place it. In this case, you can randomly shoot the ball, or
you can, yes, but we did not do that, because what we wanted to do here, we wanted to replicate the simple reaction task. If you move the machine,
the same side.
yes, because if you move it, then you would have some kind of choice reaction task. And the problem is you cannot mask the motion. So we try that, we try to camouflage all these different things. You will always see that. Okay, so if it moves, even if it is just half a second before the ball flies out, you will know where the ball is going. Okay,
And then
so
they knew in which direction they react.
yes, yes. Okay, so in that case, the solution would be 2 ball machines. Okay, so that is the only option. You have 2 ball machines, and then you do not know, okay, which one is putting out the ball. Okay, so orientate them like this. And yeah, we tried that in another experiment, not with 2 ball machines, but with the motion, and they were always able to anticipate it. Okay, so the reaction times were 50 milliseconds or something like that. It's not possible without anticipation. So, yeah.
Just another comment I had here. We were struggling very much with this, motor-related orbital potentials, checking this N1 or N2 amplitude. I would assume that, if it's quite connected, so if you move from the empty area and then you go towards the central region where you start to find the motor-related orbital potential, that would correspond somehow with this amplitude. It transitions from the more occipital or let's say parietal level towards the central one. So
yes, we have not investigated it in this study actually, because in this study we had the problem also of the lower signal to noise ratio. Okay, so obviously you can also see this in the amplitude. The amplitudes are still quite high, but the signal to noise ratio is way lower, and we had more trials also in here. Okay, so we do not have the full field stimulation with the circles. We only had this very small ball that was flying out. Okay, so it was a bit harder. However, if we come to the lab experiments, what we have seen is that in addition to the motion onset visual potential, okay, so the N2, you also have the potential in the pre and supplementary motor area BA6. So we have called it at that time, because there was no description of this potential, we have called it BA6 negativity, because it was a negative potential. And that negative potential occurs earlier than the N2. Okay, so this negative potential occurs around 140 milliseconds, okay, 130 to 150 approximately. And that corresponds quite well to the TMS studies that have interfered with BA6. If you're doing it in that time frame, your reaction time is delayed. Okay, so there's some kind of processing. However, it is way earlier than the visual potential. And in contrast to the visual potential, it is only stimulus locked. It is not time locked. Okay, which means that after the stimulation, and this is what you also find in anatomical studies, for example, you have some kind of connection to the motor areas. This is also the hypothesis is from an evolutionary perspective. You see something in your environment and you activate your motor areas because maybe you have to run away from the tiger. I don't know. Okay, so this is the one potential that you have. And then it seems that you are some kind of pre-programming your motor response because it's a simple task. It's always the same response. However, initiating the response depends on the perception of the motion information. Okay, so it depends on the N2. This is why the BA6 negativity is only stimulus locked and not response locked. Okay, so you have to, let's say, wait until your motion system identifies the stimulus as motion, and then your response is triggered. That was at least the conclusion that we drew from that. And there are some animal studies as well on that. So there are some studies with monkeys where they also have investigated the motor system and the different timings. The TMS study would be another example. Okay, so it seems that it is more dependent on the motion system in that case.
then really, if you would be like logged into the response, then you would need to eliminate this potential out, and you need to see clear response log potential.
For the motor part, you mean? Or for the motor part, we did not identify that.
So you didn't
So-
process or you didn't identify?
We processed that. And for the lab experiment, there were some movement-related cortical potentials, but not for that experiment. We could not find it in there. It could be related to the signal-to-noise ratio. I don't know. There was some kind of activity, yes, but I would not be able to identify, okay, this is a certain potential. Okay, so that was way harder.
Struggling with those potentials, so we know. Okay, interesting.
Yeah, so the motor part actually was really hard. So when we had for the first study on the visual system, one of the reviewers was interested in all the movement-related cortical potentials and things. So we were investigating that, and we were able to identify them, but they were way less clear when compared to the visual potentials. Okay, so there were potentials that were corresponding to the ones reported in the literature. But still, the identification was way harder of these potentials.
That's always the case, and we will always struggle sometimes, even if you go to the lower limb, could be because it's down there in the
sulcus.
yes. But it should be for the right and left hand quite specific, and the C3, for instance, contralateral, the right hand, right? But yeah, indeed, it's not that visible, not clearly visible as it is. So we still struggle with this idea and never managed to come to the conclusive, let's say, findings.
Yeah, I think it also makes a difference if you have self-paced movements or if you have externally triggered movements. Okay, so if you have self-paced movements, movement-related cortical potentials are typically quite clear. Okay, so you have many studies in shooting or golf or something like that. Okay, so where you decide on the initiation of the movement. Here it is externally triggered, so once you see, you react. Okay, so that could be another point. Okay, what we recently did was a study where we actually found some motor potentials for some kind of a motor cognitive task. Okay, so where participants had to react either with their fingers or with their feet to a certain stimulus or a cognitive task. And there it was very clear. So if you are reacting with the feet and you compare it to the hand condition, you have way more activity around CZ, C1, C2. If you react with your fingers, you have more activity in C3 and C4. Okay, so based on the upper or lower extremity that you're using for the task. So there it was a bit clearer. Okay, but here for the table tennis task, we were not able to identify clear movement-related cortical potentials.
Did you check individual plots, so from individual people, were the VPs and the MRCPs clearly visible in all participants?
In most. So we have to check it on an individual level, because in the end, what we compare, for example, in terms of latency is the average latency across participants. Okay, so we have to identify it for each individual participants. Typically, the dropout rate, I think, was 10–15%, I think. So in 10–15% of the participants, we were not able to clearly identify a potential. Okay, so sometimes you say, all right, there are two peaks, and now I can decide which one to choose. But if we were not sure, then okay, then we kick the participant out. Okay, so we camped the ones in where we were able to identify the potential. What we were doing as some kind of sanity check, we were then checking, okay, the mapping, where is the location? Okay, so if you have a first peak and it is clearly an area MT, and then for the second peak, it shifts to another area, then we say, all right, then it's most likely the first peak. Okay, because in terms of location, this is where we would expect that. But if there was any doubt, then we said, okay, then the participant is out, because we were just not sure in that case. Okay, that is always the issue if you're going to the individual level and not on the group level. Okay, because then you have to identify it for each person individually. That can be a challenge sometimes.
But also, I mean, it makes sense to keep the participants out, because if you leave them in, they're just increasing the noise in the data, right? But then on the other hand, this is the this is the sample that you have, and shouldn't this also be added into like the grand average, because they also belong to the population, these individuals? And yeah, I don't know, it's more of a conceptual question, like what's a better approach to do?
Yeah, we have done that in a study where we have calculated the overall grand average and the, let's say, the reduced grand average, excluding the ones who were not included because of we were not able to identify something, and they more or less look the same. So they are more or less congruent. We had, I think in that study, we had 30 elite athletes, if I remember correctly, 30, 35, and we have excluded 3 or 4 of them. And in the end, the potential, the grand average looks more or less the same. So there was not a big difference. And this is also just for illustration. Okay, so it's not for any kind of statistical analysis. In the end, we are analyzing with the data that we have and that are reliable, where we have a clear potential, where we have an end-to-end latency, end-to amplitude, and then we are running the statistics on that. All right. So now a bit more into the direction of applied research, let's say, so a bit out of the lab. But again, important here, the signal to noise ratio was way lower, unfortunately, but not surprisingly. So it took a while to run this experiment. What we then also did, and I think I've mentioned that also before, we were interested in training the visual system. I think that was part of my response to the question in the first part, where it was more, okay, how or can you use this visually evoked potential somehow for practical application? And we were running a study on that where we used these shutter glasses. Okay, so these glasses that change between clear and opaque states. And we were again having elite badminton players. Okay, so from the 4 national training centers in Germany, we just subdivided them into an intervention group and a control group. And the intervention group had these shutter glasses. The control group were doing the same type of training, just without the shutter glasses for 10 weeks, including a 6-week retention period. And we were doing a visual motor reaction task with the EEG. Okay, so the classic N2 and so on and so forth. Some other things, but that are maybe not of interest. So just maybe have a look at the results. So you see on the left, that is their behavioral performance. Okay, so that is the reaction time. We have no change in the control group, but a significant improvement in the intervention group. So interaction effect, positive for the intervention group, indicating faster reaction time after the training. Again, we are talking about 13, 12 milliseconds. Okay, so for badminton, that is quite a lot. And even in the retention test, it was still significant. Okay, so even after 6 weeks, it seems that you do not immediately return to baseline. But the more important part was then to correlate this with, and here we are just focusing on the latencies. Okay, so the latencies of the visual evoked potentials, again, with these circles that are moving in and out. And we were calculating this within subject, and we were calculating that between subjects. And again, we found quite a good correlation here. So it explained around 64% of the variance. So changes in the reaction time were to 64% explained by changes in the latency of the visual system. Okay, so we just combined here the stimulus and the response lot N2, okay, into one score to not have too many parameters in there. And we also compared this to the motor system, okay, just to double check that there is no adaptation in the motor system that may account for the changes in reaction time. And here it was only 0.5% of explained variance, so not that much. Was not significant, not surprisingly. And there was also no significant change in the motor system. Okay, so just highlighting also that it seems that the visual system, and here the N2 can also be trained. Okay, so that the athletes are not faster than the non-athletes, what we have seen in the first study, because they were born fast. Okay, so some kind of selection effect. but it seems that they got faster because of their training, because they are exposed to a very challenging environment. And as a result, they got faster in their reaction time. All right. So bottom line here, we can also train the visual system, which is then represented in the visual evoked potentials. Okay, so it can be a measure to identify any functional changes in the brain. Okay, so in this study, we were also using that because we had the problem of a placebo effect. Okay, because if you're wearing these glasses, then obviously you're expecting something to happen. Okay, but it is harder to fake that on the brain level. Okay, so in reaction time, yes, maybe they are more motivated. Okay, but here it's harder to motivate, let's say, your very basic processes of the brain. Okay, so it was some kind of control for the placebo because we were not able to placebo control that. All right. And maybe one last study, and then I'm finished with that. Just also identifying the effects of the stimulus phase on the visual evoked potential, because typically what is investigated in the literature is the amplitude, it is the latency, what it does depend on, but what is not investigated typically is the phase. Okay, however, there is the concept of perceptual cycles. Okay, so I think Ben Rodland has this some years ago, he presented that concept. And that concept is based on the assumption that and we see that in the EEG and especially for the alpha rhythm, we have constant changes in the excitability level, let's say. So we have phases where we have a higher excitability level and we have phases with the lower excitability level. So the assumption is dependent on the excitability level, when a stimulus arrives, especially at the thalamus, it is faster or slower transferred to the primary visual cortex. Okay, because if you are at a higher excitability state, then the transmission will be faster. If you are at a lower excitability state, then the transmission will be slower. Okay, so that is the concept behind that. There were some studies on threshold stimuli. Okay, so that identified that if you have visual stimuli at a luminance that is so low that you can barely see it, that you can see it more often if it arrives at a high excitability state than compared to a low excitability state. Okay, and here we wanted to do the same for a visual evoked potential. Okay, because until that time, there was no study investigating that on the brain level. There were a lot of studies investigating it on the behavior level, but what about the visually evoked potential? Okay, so we were using here the visually evoked potential for the contrast VEP, so these chessboards, black, white, because we said, okay, this has a higher signal to noise ratio. Okay, so if we split the motion, then we were not sure if we really get the signal that we want. So we were using here the contrast visually evoked potential. What we were then doing was just, okay, every potential or every single trial was, let's say, arriving at a certain phase. Okay, so we used the phase at stimulus onset. Obviously, this is not the phase on the thalamic level. Of course, we cannot measure that with the EEG. Okay, so we were just using some kind of anchor point. And we said, all right, based on the phase at stimulus onset, we were just ordering these individual trials to two different categories, let's say, okay, based on this circle that you have here. So we said, for example, from 0 to 180 degrees, we are going to one category, and from 180 to 360, we are going to the other category. Obviously, we did not know where, let's say, the threshold between changing between inhibition and excitation would be. If it is 0 to 180 or and 180 to 360, or if it is maybe 90 to 270 or something like that. Okay, so we were also shifting that. Okay, so in different directions that we are covering different phase angles. Okay, and then we sorted all these individual trials to either the excitation or the inhibition part. Okay, and that is what we then got in the end. Okay, so on the, or starting on the left side, on the x-axis, you see basically the phase offset. Okay, so 0 means that we have split it 0 to 180 and 180 to 360, and then we just had a certain offset. Okay, so 10 to 190 and 190 to 10. Okay, and then we shifted that because we cannot measure the excitability level directly. Okay, so we do not know what it would be at the thalamic level, so we just use different offsets. And we see that at some of these offsets, we have significant differences in the latency of the VEP. Okay, so this is just phase 1 and phase 2, okay, both corresponding to 180 degrees on this sine wave. And we see that we have significant differences here. However, you also see that these differences are very, very small. Okay, so we are talking here about 0.1 milliseconds or something like that. It is highly consistent, okay, so it is statistically significant in the end, but from a practical perspective, it is maybe negligible. Okay, and we cannot control it anyway. Okay, so we cannot control our brain rhythm and excitability state. Okay, nonetheless, it was interesting to see that we have basically this concept that was introduced as perceptual cycles does really reflect also on the neural level, even though it is just a very small difference. We did the same also for the reaction tasks. Okay, so here we subdivided, or we did basically a median split, the fast reactions and the slow reactions, and then identified the phase angle at the point of visual stimulation. Okay, so just to see if the phase angle is significantly different between the fast reactions and the slow reactions. And again, there was a difference. So for the fast reactions, we had an average phase angle of 23 degrees. And for the slow reactions, we had a phase angle of 266 degrees. Okay, so again, running a statistics on this data, so circular statistics on that data, revealed a significant difference, although you can see that the phase locking factor here is quite low. Okay, so the phase locking is not too strong. So we have to interpret these results with caution. Okay, nonetheless, at least it indicates that there seem to be also a phase dependence for the reaction. Okay, not only for the perception on the left side, but also for the reaction. Okay, so that was quite interesting to see. In the end, it was just more or less, it was just for fun experiment, just to see if there's something based on this concept of perceptual cycles. But it seems that there is something. Okay, nonetheless, again, the practical relevance is maybe marginal. Okay, so the differences are so small. If this then really translates into your behavior is a completely different question. Okay, and again, you cannot control that. Okay, so your excitability state at what the stimulus arrives at the thalamus is completely random. Okay, so you cannot control that. Good, but just to introduce a bit also to the phase of the signal, how the phase affects in the end your performance. So since it was a lot of information, I'll just try to to summarize all of that. Yes.
I really like that study. Did you publish that already?
Yes. It's I think 2018 Neuroscience Letters, something with alpha phase. So
you fit the data just to alpha?
No. So we were running wavelets over that. So I tried to remember exactly what we did. So we had two different wavelets. So we had a wavelet with a C of 3, so with a Morley parameter of 3 and another one of 5. So one for the temporal resolution and the other one for the frequency resolution. So we identified the frequency of maximum phase locking. Okay, so yeah, frequency of maximum phase locking. I don't know how to explain this differently. And then in this frequency layer, we identified the phase. Okay, because theoretically we could identify the phase for all frequencies, but we thought, okay, if it is a frequency of maximum phase locking, then it is a frequency in which the signal is processed. Okay, so we first had C of 5 for the frequency, and then we had a C of 3 to reduce the temporal smearing to get the phase for the stimulus onset.
So basically every participant or like every data time series had a different frequency.
Could have a different frequency, yes. Most were clustered somewhere between, I think, 10 to 15 hertz, because that was typically the frequency for the phase locking of the VEP. But theoretically, yes. we did a control analysis in the alpha frequency band. So we identified for every person also the individual alpha peak frequency. Okay, so the maximum synchronization frequency in the alpha range, and we were running the same analysis, and there was no difference. Okay, so doesn't matter it was what phase offset, there were no differences between the two phases, indicating that it is not the alpha frequency, but it seemed to be the frequency of maximum phase locking. Okay.
If I understand correctly, the kind of conclusion that you look at the phase orientation of different frequencies, because at the same time interval, you know, one phase of one frequency can be higher than since you did that analysis, the phase of another frequency that is like slower or faster, and you know, they are not, it's hard to align them.
Yes, that is true. But in the end, somehow we have to find a frequency as an anchor point, let's say, because we cannot use every frequency. So we use two anchor points. One was the individual alpha peak frequency, because the concept of perceptual cycles is based on the alpha frequency. Okay, so we said, all right, maybe this is the frequency where this, or the differentiating between the phases could have the strongest effect, because it is a basis of the perceptual cycles, or alternatively, it is the frequency in what the stimulus is processed. And that is, or that was the frequency of the maximum phase locking. Okay, so we calculated the phase locking factor, and the frequency with the highest phase locking factor was then used for the subsequent analysis. Okay, nonetheless, I agree that, of course, if you have a frequency of 5 or 10, then you have twice as many cycles for the 10 participant. However, in the end, then we said the distribution of excited states and inhibited states, it's still 50-50. Okay, so the probability that you end up in the one state or the other state is the same for both. The periods are just longer.
Yeah, that's true.
This is also why we said, okay, this is nothing that we can consciously control. Okay, and we also do not know if the alpha rhythm in the cortex, what we can measure, is the same as the alpha rhythm in the thalamus. Okay, so yes, there are some indications that there are connections, but there are also indications that there are none. So this would then be the pacemaker neurons.
Yeah, I also think it's much, so normally thalamus is connected with the alpha rhythm.
Mm-hmm.
So it's really hard to say that if you take the phase lock, the maximum frequency of like the maximum phase locking frequency at 20 hertz, it's hard to say it's the same function rather than, but yeah.
We cannot say that anyway, and we would not say that anyway, because we cannot measure it. So yeah, in the thalamus, it's typically around the 10 hertz, which corresponds quite well to the individual alpha peak frequency. This is why we used that as the second anchor point. However, there was no effect. Then we can start speculating why that is the case. Nonetheless, we just have this information from the thalamus from animal experiments, because there you can measure that. For humans, at least at that time, there was no study on humans directly testing in the thalamus. It's maybe a bit dangerous. So. Yeah, but I would not trust to validly measure the thalamus, to be honest, because it's quite deep in the brain. So,
like, but sometimes they have patients that need this. So.
For the thalamus, I just know it for the subthalamic nucleus. But anyway, of course, there are a lot of uncertainties, and this concept of perceptual cycles is based on behavioral results. Okay, so you have some kind of behavior. So you see a certain stimulus more often if it arrives at a certain phase measured at the cortical level. And then you try to argue, all right, maybe it is associated with the thalamus, because we know that thalamus and cortex are connected. But of course, this is always something you cannot directly measure or find direct evidence. So it is just an assumption that you have in the end. That's true. That is why it was more a just for fun study, let's say, or analysis. Question?
Yeah.
Yes, yes. Sorry, go ahead with your question.
Can you unmute yourself?
I am unmuted.
Like the sound.
Can I not change it? No, it's not.
Yeah. Abdul. Abdul.
Hello?
Abdul, to repeat the question.
Okay. Abdul, can you repeat your question if you already asked? We did not get it here. So please just repeat what you want to know.
Yeah, microstate analysis, is it possible in this kind of study?
So we have not done that, but theoretically you can try that, but we have not considered it for this type of research. So this was really just about the phase of the signal, but we did not go further because, as I said, it's very hard to draw definite conclusions because we have the assumption with the thalamus and we do not really know what is going on there. Okay, so we stopped at that point and did not go further into detail. But theoretically, you can try that, but we have not considered it at the moment.
Okay.
All right. So maybe just as a summary, as I said, that was now a lot of information, I think, but to sum up maybe the most important point. So the VEPs, what it is about, what we can use the VEPs for. Basically, they provide us insights into the functional properties of the visual system. Okay, so obviously about the structure, we have no idea. We can just conclude that if there is some kind of deficiency, as you've seen in the macular degeneration patients, that there is some kind of structural underlying reason. But here we are really focusing on the function of the visual system. We must consider the characteristics of the visual system. Okay, so when you are using VEPs, you have to think about in advance, what exactly do you want to investigate? Okay, so are you more on the P cell level? Are you more on the M cell level? It is more about luminance contrast, color contrast, or motion. And then you have to define the stimuli accordingly. To investigate that for the VEPs, typically you find most of the components, especially the N75 and the P100, in the primary visual cortex, so V1, while for motion, it is mostly in the motion sensitive area MT, so the mid-temporal areas. The VE experiments must be highly standardized, should be highly standardized. Okay, so as I said, they are very sensitive to any change in environmental conditions. We have seen this in our table tennis experiment, that the signal to noise ratio massively dropped, and we needed many more trials to really get a clear signal. This also relates to the next point, that for a valid VEP analysis, this requires sufficient signal to noise ratio. Okay, so there is no definite number of stimuli that you need. Okay, so it depends on the situation. ISCEV standards for the contrast, so the chessboard would be 50 in a highly standardized setting. That is, let's say, the best case scenario. However, if you're doing this in a more ecologically valid environment, you have to increase this number. Okay, by what number is hard to estimate. Sometimes you also have to try that. What we did for our experiments, we had some test runs where we tested different numbers of trials to figure out, okay, what is required to have sufficient signal to noise ratio. What we investigate typically in a VEP are amplitude, frequency, or phase. Frequency not that often unless you have constant visually evolved potentials. Okay, however, amplitude, let's say the responsiveness, or sometimes neural investment, depends on in what fields you are working. The latency, of course, okay, so the latency here, very important, especially for our studies with the athletes. So as an indicator of the speed of neural activation of the visual system, and the phase, what I presented in the very end. Okay, so maybe differences in the processing dependent on the phase the signal arrives. Okay, although with the limitations that I have just indicated. We can modify the VEPs, so it is nothing that is, let's say, fixed, but it can change based on, for example, training, as indicated in the study with the badminton players, especially related to the latency. Okay, so in amplitude, there were no differences. We can measure VEPs in sport-specific settings. Okay, that was the example with the table tennis athletes returning balls played by a ball machine. Yes, we have to consider the lower signal-to-noise ratio, but it seemed to be possible in a more ecologically valid setting. Okay, so that makes it maybe even also transferable to some kind of outdoor activities or whatever. Nonetheless, this is something that needs to be tried, obviously. And last but not least, the phase part. So the last study, yes, it has a significant effect on the visually evoked potential, at least for the contrast one. However, we have to consider that first, we do not exactly know why that is the case. We can speculate with the perceptual cycles, yes, however, we cannot directly measure. And it seems that the practical relevance is marginal in the end, because the difference here, we're talking about 0.2 milliseconds. Okay, this is very, very small. It is hardly possible that this really translates to some kind of reaction, something like that. All right. These are maybe the most important points. I hope I did not forget anything, but thanks a lot for your attention. I had a slide for that. It does not work. Ah, there it was. Okay, there it is. Wonderful. Thank you. All right. Questions left or something?
Yeah, I'm checking online. There are any questions, but
there is a hand, or there was a hand.
No, there was a clap.
Ah, there was a clap. Ah, okay. I just saw something yellow in my peripheral field of view.
Really nice. Thank you, Thorben. Perhaps one thing, if it's not directly there related to the studies you've shown, you know, the information here for Anna and Tisa, they could, or everybody could see even online, really nice trajectory that you showed, basically from the very initial studies you started, and then, you know, to the last studies that you're still thinking that are connected to the first studies that you performed for your PhD, for instance.
Yes, yes.
So can you give them, let's say, some advice, since they are at the beginning of their, you know, career, how to orientate and then think? So at the moment you were, you know, publishing the first studies, did you think already about the, you know, behavioral changes and then longitudinal designs, things like that? And how come that you managed to stay in contact or basically connected to the original research you've done?
Yes, it was actually the idea from the very beginning, because well, the major challenge was to convince the athletes and the coaches. So, and when I was talking to them, I had to provide them something, okay, some kind of practical outcome, because the question was, okay, I need your athletes 2 hours, they're sitting in front of a computer screen and pressing a button. And typically the response is, okay, are you an idiot? We are going on the court and we are doing some training. So that is why the initial idea was already, all right, see, what are we doing in strength? What are we doing in endurance? We are doing tests with the athletes. If you have a marathon runner, the marathon runner is not always running a marathon. Okay, so in regular intervals, the participant is coming to the lab, running on the treadmill, you're measuring gas and lactate and all these different things. Why are you doing that? Because you can improve the training. So I went there and I just said the same. All right, I want to have your athletes. Okay, I want to sit them in front of a computer screen and doing tests with them. Yes, I know this has nothing to do with your sport, but you are also doing tests on a treadmill, for example. It has also nothing to do with your sport. Okay, I'm doing that because I want to know what is the difference in the athlete's brain? What does adapt? What do you have to train? And once I know that, I can tell you, all right, what type of technology may we be able to use to improve the athlete's performance? So I think at that stage, it was some kind of a must to already have some kind of practical application in mind. If that in the end worked or not, was a different question, because at that point, I didn't even know if there would be any differences in the athlete's brain. It was just an assumption. If it was, or if it would have been, there are no changes, then I would not know how can I train it. But at that point, and that was a time-consuming part, was to find also the arguments for the athletes and coaches to convince them, all right, this is a study that we can do. Because overall, from the first study starting, I think it was in 2014 or something like that, to the last study, which was 2021, that is quite a long time interval. So it took us around 5, 6, 7 years to run all these different projects. Mm-hmm. And so it was also very nice of them to provide me the time and do the test with their athletes. But the more we did, the more they also understood, okay, this is something that we can train, and they were more and more supportive. But in the very start, that is something I think that you need to know in advance, and how to convince the athletes and the coaches. That was maybe the most important point. And that is also something that I realized, and this can maybe also some kind of helpful information, hopefully, always to have the practical application in mind. So what can you do with that? Because if I would develop something that only works in the lab, an athlete would have to come to my lab to do this type of intervention or test or whatever, they would never use it, because they are all across Germany and I'm in Luxembourg. They would not come to me. Okay, so this would not work. So it must be some kind of practical application. What do you want to use it for in the end? Okay, so what is the end product? For us, it was then training recommendations for the clubs. They have it now there. They have it printed, shutter glasses. These are the parameters. This is what you measure, and they can now do that. If they do it or not, at that point, it is not my problem. I try to convince them that this can be helpful, and I hope the study support it. But if they are using it, it is now their responsibility. But they have this information, okay? And we started with, you're sitting in front of a computer screen, and ended up with, okay, here are the shutter glasses, train your brain with it, and then hopefully win the Olympic Games. So yeah. This is maybe a bit too ambitious, but
nice. So we were just discussing yesterday, for instance, like, you know, the parameters that we are going to explore with the new data sets and so on. So did you initially explore the area? So you mentioned the fMRI studies, the animal studies. So was that something that you kind of like found yourself, and then based on that, you created a setup and then constructed the paradigm, contrast versus, you know, expansion and so on? Or was it like just you had it ready over there and then you took it and then did your tries?
No, it was something that I had to explore, because in my master thesis, I was investigating more balance-related things, so continuous and event-related balance, perturbation, and neural response. And initially, I wanted to continue with that during my PhD. However, I was not allowed to, because I was not allowed to continue with the same topic, even if it would have been another study. So I was just thinking about, okay, what is another interesting field? And as I was playing badminton also at that time, I was just thinking, all right, what is their performance profile? What are the demands in that sport? And of course, I wanted to link it to EEG, because I was working with that since my second semester in the bachelor of things. So I was just checking, all right, what about the visual system? The visual system is the dominating one. What do we find there? Then I checked the literature, and I just found, all right, they were all doing pattern reversal visual evoked potentials. And I was always wondering, why are they doing that? So why are they investigating contrast information? This is not what you need on a court. On a court, you need motion. And then it was, okay, 2 studies have differences. 2 other studies have no differences. Sometimes you have differences with a small check and not with a large check, and no one has an idea why. So I said, all right, I want to validate this, let's say. I would do the same experiment with the badminton players, and then also read it the highest level, not intermediate level or whatever, but the highest level, but include also the motion, because from the beginning, my idea was, okay, I should find something in the motion and not in the contrast perception. So that was the initial idea. Okay, and then I just checked with the studies. So primary visual cortex was not that complicated, but then for the motion sensitive area in T, okay, where do I find that? How can I investigate this with EEG? Do I go, for example, with a dipole and handle this, or do I go with a CSD? In the end, I decided for CSD because I wanted to stay on the channel level. Also, in terms of practical application, if they would do an EEG later on for whatever reason, at their clubs or something like that, they would never do something like dipole analysis or things. Okay, so just to have it more applicable also to practice basically.
Yeah.
And
so
yes, then we developed from there. So for example, I did not know in the beginning that I would use shutter glasses at a certain point. Okay, so it was all right. It is the brain that adapts. Okay, in the athletes, it is the visual system. So we have to train the visual system. So next step, how can we train the visual system? But that came later. It was not defined everything in the beginning.
So the take-home message, I think it's sometimes clever, or at least I think it would be necessary always to think from the perspective of usability, or how you can then translate that into practice, not just take the paradigm that was developed in the lab and was used forever, but nobody knows why exactly, right? So this was many times the case also in our studies. We presented just the blink because it was convenient, right? But we said, okay, it's the most simplistic way of presenting that.
Yeah, I think there are also different fields. Okay, so I don't know if someone is working in the field of sport, but if you're working, for example, with patients with different diseases or something like that, how can it help them in the end? Okay, so once you know how certain parts of the brain are working, how they are responding to tasks, what can you do with that information? Okay, so that was always the question. How can I go on with that? Apart from knowing, all right, this is how it is. Because this is, again, that was the first question of the coaches when I presented them the results of the first study. All right, we see differences in the athlete's brain. They are faster when compared to non-athletes. There's all right, that makes sense. So what? Okay, they are faster, nice to know. All right, we do not want to know that. We want to make our athletes better. Okay, so, and then there is some information needed. All right, how can we use that? Okay, and then say, okay, wait, we have an idea. Once we know what we have to train, we can think about how to train it. Okay, and again, it's always, I'm also telling this to student, it's the same example, because also the students, they are always struggling with brain and these things. They know a lot about endurance and strength, and it is always the same principle. You investigate something and use the information to design your training. And here we are doing the same. Okay, so why are you doing maximum strength training, strength endurance training, hypertrophy training, and all these different things? Okay, because you know that this type of training has certain adaptations. And we have to do for the same for the brain as well. Once we know what to train, we can think about how to train it and then see if it works. Okay, and then we can do stroboscopic training for the visual system, or some kind of cognitive training for the prefrontal cortex, or I don't know. Okay, so this will be then the long-term vision. This is only what we did, is about reaction time. It's an important component, but it's not everything. Okay, so only if you have fast reactions, you will not become a good badminton player. It is essential to become one, but it's not the only part. Okay, so there are other things that needs to be investigated in the future.
Yeah, great. So I guess in the second part, then after the lunch break, we will be investigating or just trying to analyze some data sets that were collected with the aim to see if there are any differences occurring when you expose a participant to prolonged inactivity, which would be super interesting again to see the comparison, like the contrast versus the
motion.
Yeah. So let's see.
Yeah, that's fine. So the first presentation was longer than expected. So, but yeah, we will do the working with the data set then later on.
Okay. So if are there any questions, comments? No. No. Okay, there's the time, but in general, I think we can conclude here. We will be back at 1:30, right? So yeah, thank you again.
Yeah, thanks a lot. Thanks.